And
Okay, since
yeah,
we don't have any other question, so you can hold the station and move on to your next
yeah,
presentation.
okay. Can you see my presentation? Okay. Yeah, my previous presentation is for challenging, and this presentation is for my paper presentation. Uh, my name is Yong Kwan, and I'm here to present my paper, Task-Driven Deep Image Enhancement Network for autonomous driving in bad weather. So we address the problem of visually enhancing driving scene in bad weather you're currently facing. It is perceived as an essential key step towards visual perception and serves to eliminate the gap between the resulting performance and the visual reasoning capability of human beings. For us, it might be easy to understand the driving scene for visual perception under clean weather environment. But a neural network model in the bad weather scene, this might be quite challenging. Uh, so why is this? Where the success of deep convolutional neural networks relies on a large number of high quality images and a large computational cost on large scale resource devices. However, existing models do not typically consider the degradations taken from bad weather conditions for training, as well as low resource devices to be deployed on mobile devices. So we need to train complex visual degradation caused by bad weather with DNN having lower resource consumption. A solution to this difficulty is to employ image enhancement methods as a pre-processing step. Benefited from these methods, the latest recent in learning-based enhancement models seem almost plausible at first glance. However, unfortunately, we observed that existing enhancement methods still not suitable for high-level vision tasks in bad weather, and even worsen performance in some cases. So first, they usually rely on metrics based on the human visual system. And second, they generally require a lot of computational power despite having to run autonomous driving with resource-limited platforms. For bad weather enhancement, many models and algorithms have been developed to deal with only one weather conditions. However, they are not designed and trained for all the bad weather conditions, therefore may not guarantee to build safe visual perception in bad weather. Moreover, their methods are computationally too inefficient for on-device embedding, so not is suitable for fast inference. To the best of our knowledge, our work is the first study to provide fast processing time and compressed parameters while being perception and hardware friendly to deal with a variety of bad weather conditions. When high-level vision tests are conducted in bad weather conditions, and then they often encounter in image enhancement is a very key step usually, which might be poorly related to the task-specific goal. Recently, limitation of deep learning-based high-level vision models has been investigated to reveal their inefficiency against bad weather conditions. However, most models still consider some weather effects, such as rain or fog, separately. In addition, their optimization is still not suitable for high-level vision text, and there is no consideration of the inefficiency of the hardware. So can you do something else to alleviate this problem? In this paper, we introduce a novel task-driven image enhancement net framework that is benefits from exploring the mutual influences between visual perception and image enhancement for reliable visual surveillance and visual perception in bad weather conditions. To this end, our model aims to have perception and hardware perception-friendly and hardware-friendly characteristics against any bad weather situation as end-to-end running optimization. To the best of our knowledge, this is the first attempt to connect image enhancement and high-level vision for visual perception under multiple bad weather conditions. Our network is inspired by DenseNet as a feature encoding network. Our enhancement network can be divided into two components. First is a harmonic dense block named HBlock for low memory computational cost. And second is feature identity extraction model named FIA with feature fusion high-level perception task. For HBlock, in order to achieve more high-quality recovery, a recursive enhancement structure is introduced with a total of 3 stages. And FIE is designed for correlating information from image enhancement and high-level vision perception features. So the FIE connects them by representing the mutual influence between image enhancement and visual perception in a unified framework. To run the proposed network, we further integrate both first image enhancement network and high-level vision perception network via 3-stage. So the first, we illustrate image recovery loss. Existing MSC mean squared error optimization usually produces blurry visual information, which results in perceptual unsatisfactory images with over smooth content. To prevent this, we estimate the successive approximation to the bad weather distribution with the guidance of Chevenier penalty function, which is more robust to outliers and smoothing elements. And next, we use high-level, second is we use high-level task loss LHT from a pre-trained high-level vision task network to provide the enhancement network with connectivity that promotes it to be perception-friendly. By default, perception networks for high-level vision tasks are pre-trained on benchmarks composed of clean images and are frozen while running the proposed framework. As far as we know, this is the first study to run a variety of high-level vision tasks while dealing with all the bad weather elements. And next, loss is feature identity loss. This loss is to convey more strong perception-friendly property. So we describe the feature. We describe this loss, and this loss is to give the relevant information in the training process. So we propose to use hypersphere space. So based on the above illustration, we incorporate the above mentioned losses as an objective function. We optimize the total objective function based on the stage-wise manner and can be trained by the following function. A and B, alpha and beta are trade-off coefficients of the LHT and LFI respectively. So this is the data set for training and validation. For the synthetic data sets, in order to, we adapt raindrop, and haze simultaneously on each image in the data set. And for rain detection, mode depth, and object detection, we utilize two simple Kitty and RID datasets respectively. And all the reported implementations are based on the PyTorch frameworks, and our methods has done on one NVIDIA Titan X GPU, and one intercore CPU. Next is our experimental results. Table 2 shows that our methods achieve significant gains in terms of PSNR and SSIM. PSNR, SSIM is a very classical measure for low-level vision tests. As shown in figure 4, qualitative results reveal great effectiveness, while the results by the raindrop still contain visible bad weather elements, such as the visual quality enhancement by our methods is better than existing methods. To evaluate the effectiveness of our enhancement framework on high-level tests in bad weather environments, we further show the method yields meaningful results. Please see table 3. Table 3 means our methods outperforms the high-level perception performance in comparison for different methods using ResCan, draindrop, PRNet, and PRNet as a pre-processing. Most models do not improve over the bad weather input in terms of high-level perception metrics. Instead, our method is observed to improve performance in higher vision tests without deteriorating. This proves that our methods represents mutual influence between visual perception and low-level image enhancement or restoration. So therefore, providing significant help for bad weather capabilities. Figure 5, 6, and 7 also show that our proposed model outperforms the existing methods. And lastly, for additional analysis, we investigated computational cost analysis, aberrations. First, table 4 reports the computational cost of our enhancement network and some state-of-the-art methods. From the results, we can find that our methods has less computational overload due to the harmonic dense block named H block. Considering their hardware-friendly ability, it is appealing to still maintain perception performance when facing bad weather images. Also, to study the contribution of each network in proposed network, we alternatively remove it and identify the impact on the high-level perception performance. As can be seen in tab 5, our methods with joint training option C to D performs better than simple connection option B. Joint training option C has a slightly lower baseline in task 1 and task 3, which is not surprising because it was not trained with the feature identity network, but proposing feature identity network option D, our method is best ranked approach that significantly outperforms the other 3 options A, B, and C. And we are encouraged to observe that the FIE brings the interconnection between the 2 networks. Okay, this is our visual results, and I'm going to conclude with some additional research on some very complicated and challenging images. So here's one. We generally address multiple bad weather degradations. Despite of this fact, we're getting pretty well enhanced images. Our performing perception performance and the number of errors is pretty minimal. Okay, and this. Thank you for listening my presentation. Yeah, and any other question?
Okay, guys, if you have any questions, so Yun-Kwan is with us. You can write your question in the Zoom chat window, and I'll ask it for you from Yun-Kwan. So one question from my side, Yun-Kwan. So which data set you have used here?
Oh, sorry. Can you?
Which data set you have tested on?
I tested 3 data sets. First is rain detection for 2 simple benchmark. Second is Kitty data set for mono depth estimation, and last is RID data set. That data set was published in CBPR 2019 for object detection. Yeah.
There is another data set, recent one, published in probably 2020, nuisance data set. They also have quite extensive videos for bad weather, night scenes. So you can also try your algorithm with that. Probably it will help to analyze that, how it can incorporate or how it can perform on the challenges which are presented by nuisance data set?
Yeah, a good question. Actually, you said that nuisance and any other recent autonomous driving data set has bad weather elements, but their ground truth, acquiring ground truth is very challenging elements. So unfortunately, I synthesize synthetic bad weather elements on existing clean weather data sets. But this, what you say is my future work and my future plan. Yeah.
Okay, thank you, Yunkan, for a valuable discussion about the challenge and your paper. So with this, we'll move on to our